The goal here is to use Newton's method to obtain a solution of an equation, this one being sine x equals x over 2, and to get some insight into what Newton's method is really doing. To begin, I'm going to draw a graph. So I'll type sine x, and by clicking on this I get access to some tools in this pop-up menu. This is a plot builder interactive plotting tool. So there's a graph of sine x from minus pi to pi. Now I'd like to add the graph of x over 2 to that existing graph, so I just drop the expression onto the existing graph, and we can see there are 3 intersections, and that represents 3 possible solutions. This solution would be x equals 0, and that's clearly a solution. Sine of 0 is 0, so 0 equals 0. There's a positive solution here and a negative solution here, and I'm looking for this positive solution here. Now, one way to get the solution approximately by reading off the graph, here I've put a grid on the graph to help try to read the coordinates. Another way would be to use the probe itself, which becomes a crosshair, and put the crosshair on the point and attempt to read the coordinates of this intersection. Well, having decided that, okay, this is a worthy approximation, we want to save that data. So go back to the probe info and copy the data, and then come over here and paste it. And so we have an approximation taken from the graph. Well, having gotten an approximation to the solution that we're looking for, we ought to ask ourselves, can we get a more accurate computational solution? And to do that, we'll begin by writing the equation sine x equals x over 2. And then again, clicking on the graph gets some tools. So here's a solve tool. We'll solve this numerically because there's no analytic solution. So solve numerically from an initial point. So we're starting at an initial point to begin an approximate computation. I'm going to try 1.3 as my initial point and see what happens. Okay, I have a solution. So this is 1.89. You can see our graphical approximation wasn't super accurate, and so we have now a 10-digit estimate of what that root would be. If I were carrying more digits, if I had set this to carry more digits, then I would have more places in my answer. Let's now look at Newton's method itself. Here's a statement of the method. You want to approximate a root of an equation in the form f of x equals 0. So everything is on the left-hand side. You form a sequence of approximations. These are called x1, x2, x3, etc. And the recipe for generating these approximations would be xk minus f at xk divided by the derivative at xk. That forms the next approximation. You would take that next approximation and use it in place of the xk's, generating an xk plus 2, etc. And hopefully this sequence of approximations gets closer and closer to the answer you're looking for. To do Newton's method, to implement it here in Maple, it helps to define a couple of functions. So first, the function that represents the equation, f of x equals sine x minus x over 2. and we want this to be a function, so we click on it and we pick assign function, and that has manufactured a function. I would also like to make a function of this right hand side of the Newton recipe, and I will call that one g of x, and that's x minus f of x divided by the derivative, so f prime of x is the derivative. This prime symbol from one of the palettes or an apostrophe would generate the derivative. So let's again pick assign function, and to see what that function might look like, we'll type g of x and have it reproduce the rules. And there you see the x, sine x minus x over 2 is the function f. The derivative, you can recognize derivative of sine x is cosine x, derivative of half x is a half. Okay, so there's the pair of functions that we need to implement Newton's method. Now, we'll begin with an initial approximation. So I'll take that as 1.3, and I want to put 1.3 into g. That will be the x that I start with. So g of 1.3. Hit the enter key, and we have 2.64. Now that's the first approximation I've generated. I would like to take that number and put it back into g. So g of this number, well, I could copy and paste it. I could type it, which it would be horrible, or I can use this equation label on the right to reference or stand for this number. So I bring up the insert label dialog, I put the number 3, and that represents 2.64, etc. If I hit the enter key, I will get the next approximation in the sequence. And if you were doing this for some purpose that you wanted to record this stuff and see it later, you could change that label to label reference, and then you would actually see what g is acting on. So this number has to now become the argument of g, so g of that number, and it's got equation label 4, and it generates this approximation. I want that to become the argument of g, so g of this number, so that has label 5. Then I want this to become the argument of g, so that has label 6. And if I do that one more time, I will have the number that ends in 6-7, which is what Maple said was the best answer you could give me with 10 digits. And if I do it one more time, I should get back the same number, because any improvement is taking place way out here, well beyond the number of digits I'm displaying, and so you won't see any change in those digits. And again, if you wanted to change all of these to label reference, then you would see just what it was that you were computing. Of course, in a production mode, if you wanted to generate this sequence of iterates, you might want to write a for loop, and you can do that as follows. Begin with an initial approximation 1.3 and use a new variable. Don't assign to the letter lowercase x, because lowercase x is the free variable that you have in the rest of the computations. So here's the loop for some counter from 1 to I'm going to go to 8 do. And then what are you going to do? You're going to assign to the letter x whatever you get when you compute g of x. and then end that loop. Okay, so what's going to happen is x will start out at 1.3. It'll go in here. G will compute the first approximation. It will compute this number, and we'll assign it to the letter x. Next pass through the loop, this x will be 2.64. G will compute 2.03, and it will assign it back to the letter x. And so by continuously reassigning to the letter x, you don't get this string of new variables, x1, x2, x3. There's the list generated, and you can see once you get to 6, 7 at the end here, you won't get any newer numbers unless you increase the number of digits. So something as important as Newton's method, which is one of the oldest methods for solving equations numerically, a tool like Maple certainly has a built-in functionality for this. So to access one of these tools, we'll go here to the Tools menu, and we are going to load a package. Now, a package is a bundle of related commands grouped together in the math library for convenience and for neatness. It's all part of Maple. So having loaded that package, we're going to act on the rule of this function, which I get by typing f of x, hitting the enter key, and I'm going to click on this, and we see down here on the Student Calculus 1 we have access to tools called tutors, and the tutor that I want is this Newton's method tutor. The function rule has been absorbed into the tutor. I will change the initial point. I'm going to make that 1.3. I will increase the number of iterations. Even if I make that 8, Maple will quit when it sees two numbers come out to be the same. And then I click display, and you see here the list of iterates. You see once you get to 6, 7, Maple quits, because the next one is going to also end in 6, 7, and Maple says no sense giving you the same number, you've already got it. Now what's happening here in this plot window is a graphical illustration of the theory behind Newton's method. We're starting here at 1.3, and at the point on the graph of f, which is what this is, a tangent line is drawn. This is a tangent line, and this is its x-intercept. That, see that 2.6 roughly? That is the first approximation. And at 2.6 on the function, on the graph of the function f, another tangent line is drawn. And its x-intercept is very close to 2. That's this number. And a next tangent line is drawn, but you can't see it. Now here's an animation where the tangent lines are drawn one at a time, but even then, this is kind of a small window to see that in. So let's close that. The animation is written to the worksheet, and then we can go through these frames one by one. So here's the 1.3, and there's the first tangent line, and this is his x-intercept, and that's where the 2.64, etc. is coming from. And we do another tangent line, come up here and get this approximation, which was 2.03, and then we have the next tangent line. You cannot at all see that. So let's zoom in, and let's rubber band this section to zoom in, and you can see right here there was another tangent line drawn, and if we kept going, these tangent lines would get smaller and smaller, and the approximations would get closer and closer to that 1.89. So that's the geometric theory behind what Newton's method is doing. It's using these tangent lines to sneak in on the root. Now, we can actually implement that geometric process analytically. So Maple has a tangent command. If applied to f of x at x equals 1.3, it will return the equation of the tangent line at x equals 1.3. Well, the y equals is not there, but you can imagine that we've put y equals. Okay, so now you want to set this equal to 0. We can do that. We can equate that to 0. But if we didn't, the next step Maple would carry out anyway. We want to solve this for x. That would be the x-intercept. So if we just use the solve, we would have the next value. And there's your 2.64, etc. We want to build a tangent line at this point. So tangent f of x, x equals, now we got to reference this number, so I think I will just drag it over, and there's the next tangent line, y equals. This is the tangent line, rather than set it equal to 0, because Maple will let its solve command assume that I meant to set this equal to 0. So there is the x intercept on that tangent line, and we're recognizing these numbers, 2.03, that was recognize that. Now the next tangent line, and we need this number, y equals this, that's the equation of the tangent line. We want the x-intercept, so we solve. And if now we say, instead of just saying solve, we obtain the solution for x, then we don't get the x equals, we just get the number. And so again, it's tangent f of x, x equals, and now since the return doesn't have these brackets and the x equals, we can use this equation label here to reference that number. And we have another tangent line, and we get the x-intercept on that tangent line. And you can see the 1.89 beginning to show up. Tangent f of x, x equals, let's reference this number, that's equation label 20. Tangent line, get its x-intercept, and there ends in 6.8. If we do this one more time, it'll end in 6.7, and then there's no sense going any further with this number of digits. And that was 22. And if we solve for x, we're going to get the number ending in 6.7. Having taken a look at the geometric underpinnings of the method, if you wanted to implement Newton's method and just get the sequence of iterates, there is this Newton's method command. Which, if applied to f of x, starting with x equals 1.3, if we took the output as a sequence, and even the number of iterations, we could specify suppose we do 8. This would give us a sequence of iterates, and it would go across the screen this way. If we put inequality signs that serve as wedge brackets, that becomes a vector, and so we would get this column vector with the iterates that we have seen multiple times already. Having seen the geometric underpinning of Newton's method, it's possible to use that understanding of the geometry to analytically derive that iteration formula. What you need is the equation of the general tangent line. Okay, so y equals, what is the slope? Slope of f prime at xk. And that multiplies x minus x k. And then on the left would be y minus yk, xk, yk being the coordinates at point of contact. So y minus yk. So that yk comes over as plus, and yk is f at xk. So this is the equation of the general tangent line at xk, yk. You want the x-intercept, so you have to make y be 0, so evaluate at a point and let this y become 0. And then solve for this x. So we'll solve for x. Let's take this expression out of the brackets. And I want to simplify this right-hand side, so I'm just going to grab the right-hand side. And the simplification I want is to expand, so I have two separate terms. On the left, which I peeled off, that becomes xk plus 1. And it's equal to xk minus f at xk divided by f prime at xk. So that's the derivation of the Newton iteration formula based on the understanding of what the geometry is telling us. Approximations in the process are the x-intercepts on tangent lines drawn to the function.